I would like to start with questions from homework. Does anybody have anything from chapter 15? Homework problems you want to talk about?
Why were there so many?
Yeah,
Are we
Boop.
having a chapter 15 test, or are we just gonna go on the final?
No, we'll probably do the 15 test here. Matt? 123. Sure thing, dude. Well, while I'm putting this in here or whatever, in an answer to Elisa's question, then why? Because this is kind of an important topic that should have gotten covered in Algebra 2, and I know that's not your fault that it didn't get covered in Algebra 2, not completely anyways, but we do want to make sure we do a good job of doing this because people are going to expect that you did this in high school, and I want to make sure that we can do a good job with that. I know, it's disappointing. All right, so there should be an equal sign here that just is like typoed. That probably makes one problem solved anyways. To do this though, what I'm going to start by doing is getting rid of the fractions. So I'm just going to multiply both sides by 2. Next thing I'm going to want to do is try to get rid of this negative exponent. So the way that I would do this is I'm going to just multiply both sides of this by e to the x. Okay, with that, e to the x times e to the x, I'm going to think about that just as e to the x squared. And then when I multiply it here, I'm going to multiply these two things by adding their exponents. So x plus negative x is just 0. And anything to the 0 power is 1, right? So I'm going to move everything onto one side here and rewrite e to the 0 as 1. So far, so good. And now what I'm going to do is I'm going to do a little pretending. And we're going to pretend that e to the x is just the same thing as y. So this thing that kind of looked like a quadratic before is now exactly a quadratic. Now I know how to solve a quadratic. We've spent a lot of time dealing with that. We can either use factoring or the quadratic formula. Here, this one isn't factorable. There's not two numbers that multiply to give you 1 and add to give you negative 8. So we're going to use the quadratic formula here. So negative b plus or minus b squared minus 4ac all over 2 times a. So negative of negative is positive. 64 minus 4 is 60. And the square root of 60 can reduce down to, let's see, what is that? 4 times 15, right, is 60. So 8 plus or minus, square root of 4 is 2. And then I can reduce that all down to here. But I'm not done, right? Because what I found there is just that y is equal to 4 plus or minus the square root of 15. This original problem had x's in it though, right? So now that we got the y by itself, we're going to put that e to the x back in. So we have that, and I'm going to write the plus or minus as 2 separate equations. So the last thing I have to do is to cancel out that exponent base of e to get the x by itself. To do that, I would use, what would I use to cancel out that exponent base of e? Good, the natural log, exactly right. So I'll do the natural log of both sides. And 4 plus the square root of 15 is positive, so that answer should be okay. And then 4 minus the square root of 15 is still also a positive number, so that answer should be okay. So those answers are correct. I don't remember in the end, I guess we could look at the odds. I don't remember if they made them a decimal, if they just left them as a radical. Probably made them decimals, huh? Yep. Okay, well, let's do that then. So I just do natural log 4 plus square root 15. So there's the 2.06. And then if I do 4 minus the root of 15, there's the negative 2.06. And we're good. Does that feel all right, Matt?
Yeah.
Sure, no problem. Who's next? Anybody else? All righty then. Fair enough. Today, we're going to be talking about section 1515, not 15.5, 1515. There's not 15 sections in this chapter. So here we're talking about the mathematics of finance. And we're going to talk about 3 models for that we're going to, or today we'll talk about 3 different models for kinds of problems that we can use. So we're going to talk about simple interest, compound interest, and then continuously compounding interest. So we're just going to handle these kind of one at a time. In simple interest, the interest earned is only based on the initial amount of monies invested. So the simple interest formula, FV is equal to PV times 1 plus RN over 100. FV stands for future value. PV stands for present value. That's like the amount that you invest initially. R is the interest rate written as a decimal, and N is the number of years that we're going to be doing the investment. So let's do a quick example using simple interest here. So if you invest $2,000 at a 6% interest rate, how much total money do you have in the account after 3 years? And we should probably say at a 6% simple interest rate. That word should be in there somewhere. Since we know it's simple interest, we know we're going to be using the simple interest formula. Which parameter are we going to be solving for? Future value, present value, R or N? Can somebody tell me? Future value, great, because it asks how much money do we have in the future, right? Everybody agree with that? Okay. So what is our present value going to be? 2,000, good. And our value for R is 6%. And our value for N is 3. So when I punch that all through, I get 2,360. So how much interest did we actually earn from that? 360, right? We started with $2,000. We ended with $2,360. 360 of those dollars must have been the interest then. Everybody feel okay with this? So far, so good? Just as a real life talking point, like nobody does simple interest. I don't know. It's just like a starting point. It's the least important of all these things that we do because nobody really does it. And it has really nothing to do with like exponential or logarithmic functions, but we just use it as kind of a starting place. The next situation is the compound interest. This is where the interest earned in your account can earn interest on top of it. So after the first year, the interest that you pay into your account earns interest during the second year, and then that pays in, and all the money then there earns interest in the third year, and so on and so on. Okay, so your interest, the money you earn from interest can then earn interest in the future. So our compound interest our formula is FV equals PV times 1 plus R over 100K, all to the Kn. FV is still future value, PV is still present value, R is still the interest rate as a decimal, N is still the number of years. K is going to represent the number of compounding periods per year. And most often, that K is going to be given to us in words. So if we say annually, that should mean that K equals 1. Semi-annually would mean K equals 2. Quarterly, K equals 4. Monthly, K equals 12. Weekly, K equals 52. Daily, K equals 365 would be the common ones. Okay, so let's do a couple of examples here. Yep, no problem. This one says if you invest $2,000 at a 6% interest rate compounded annually, how much money do you have in the account after 3 years? This is almost exactly the same question as what we just asked before with simple interest, right? What's the only difference? We hear the word compounded. So that tells us we should be using the compound interest model. Again, it's asking us how much after some amount, so we're looking for a future value. And just like before, the present value is still the 2,000. The interest rate is still 6. The N is still 3. The K now, what is the K going to be? How am I going to figure out the K? K is the number of compounds per year. Now that's not given to us in the as a number in the question, but rather as a word. What word is telling me the number for K? Annually. And what number is that telling us? 1. So if I go and I type this now into my calculator, I get a crazy decimal that I rounded to 2 decimal places. Why would I round this to 2 decimal places? We're talking about money, right? Why should I round money to 2 decimal places always? Pennies, right? Yeah, that's like the smallest denomination of American currency we have is the 100th of a dollar or whatever. So 2 decimal places. All right, so notice here, comparing compound interest to simple interest under the same parameters, the difference was what, like $22 or something? Woo, big deal. Well, I mean, it kind of is. It just depends on, in the short term, it's a very little deal. But over, say, let's say like 100 years, it becomes like a tremendously big deal. So if I take that same situation and I do the simple interest formula for 100 years, I end up with $14,000. If I do the compound interest formula, oops. Ugh. That's kind of a big difference, right? One situation you got $14,000, and the other you have $678,604. Woo! It's a big difference between the two. And I'd even wager to say that there was probably a situation in the compound interest scenario where in one of those years we earned more interest than the compound or the simple interest was in over 100 years. You know, like that was $12,000 of interest up there. I bet there was a year, I bet there's multiple years here for the compound interest where you earn more than $12,000 in interest. You know what I mean? So over time, the compound interest is massively better than the simple interest. Let's look at an example to illustrate how much the number of compounds per year matters. So here it says, suppose Gina invests $800 in a 7% interest rate account. How much money will she have in the account after 5 years if the interest is compounded annually, semi-annually, quarterly, monthly, weekly, daily, etc.? I'm going to just do all of this into my calculator because I'm just basically changing 2 numbers for each of these questions, and I don't want to rewrite them every single time. Does that feel okay to you guys? So I have my present value, that's 800, times 1 plus the fraction R over 100 times K. And I'm going to write times 1, even though I know it's times 1, just so that I don't have to, when I'm going to update the number, the stuff is already there for me to update. And then it's NK. So 5 is N, and then K is 1. So the first year, $1,122.04. If I instead did this semi-annually, we'll change those Ks from 1 to 2. And what I picked up a little $6.50-ish, $6.50 difference. You know. It ain't nothing, but I'm not going to write home about $6 over the course of 5 years. If I change that to quarterly, what do we pick up? Like $3.50 difference? And that's even less impressive. Although, again, it's still making it better Monthly, that's 12. So let's change those 4s to 12s. And I picked up like a little less than $3 that time. That's, well, a little more than, I should say a little more than $2. That's I'm not getting blown away here, Mr. Kulik. Weekly is 52 weeks in a year. Again, don't worry about like 52 weeks is really, that's like 364 days and a leftover day. Like, it's fine. We're just going to call it 52. What do we pick up there? A little less than $1 of difference. Boy, this is not really wowing me, Mr. Kulik. I know, guys. That's the point of this. And instead of 52, what if we change that to 365? What did we pick up? About 25 cents there or something? Whoop-de-de-doo! So the point of this is, of this problem is just to illustrate to you that like the number of compounds per month, or per year, I should say, makes a difference, but it's not like, you know, the thing that makes the biggest difference. Like the interest rate, the initial amount invested, the time it invested, all those things make much more of a difference to us than the number of compounds per year. I think typical for most bank accounts, if you have a savings account, I think they do interest quarterly. If you have a loan, like you borrowed money to buy a car or a house or something, typically the interest rate is compounded monthly. But let's do a couple of more examples where we're using these compound interest formula. So this next example says Mara has $1,000, places it in a savings account with a 6% annual interest compounded monthly. How long will it take before Mara has $4,000? I heard the word compounded, so I know I'm going to be using that compound interest formula. Which parameter am I going to be solving for from that compound interest formula? PV, FV, R, K, N. Yeah, it's how long, that was the N. Okay, so what are we going to plug in for the other spots? What's FV going to be? 4,000, right? Good, that's the future value. The PV then is 1,000. R was 6%. K is, what's K? Good, 12, because it says monthly there. And N is our variable. So we're going to be solving this equation then for N. To solve this equation for N, what should I do first? Divide by 1,000. So I'm just going to reduce that fraction as I go. And I'm going to turn that stuff, the 1 plus 6 over 100 times 12, into a decimal. That's exactly the decimal it comes out to. What do I do next? I got to cancel out that exponent base of 1.005, right? So I use a log. Good. Which based log do I want to use? I want to use the same base as my exponent. Not that it matters which log you use, but it's definitely, this one makes it the easiest. You can use other bases, but it just makes like the algebra more complicated. And like our lives are complicated enough as it is, you know? I have the threat of global warming hanging over me, this whole war in the Ukraine. I got enough on my plate. Chapter 15 test, you know, like graduating from high school, having my car's windshield get hit by a golf ball while I'm at lunch.
What?
You know, who's been chasing me in water wars?
Real.
All this stuff, like just weighing on me. Oh.
You say golf ball?
Yeah.
What about golf ball?
You didn't hear?
Is it you here?
Because Bloom's in my class last hour.
What do you mean?
Well,
What happened with the golf ball? Did it hit Nathan's car? Windshield?
You never use it. I know.
all right. So we did the log to both sides. Last thing I need to do is then divide by 12. Again, I'm going to write it like this as multiplying by 1 over 12, just so it's a little bit more clear when I'm typing into the calculator where that division is happening. The key is that it has to be happening outside of the logarithm. So I'll do 1 divided by 12 times. And then I need to use that log base command. So I'm going to press math, scroll down till I find that log base command and press enter. And then I can just type in that number there and then the 4. So that's about 23.16 years. So that's my value for n. Is that okay? Notice to solve for time, I need to use a logarithm, right? Let's look at one more compound interest example before we move on to the last model. So again, it says Gwen has $600 to place into a savings account. What annual interest rate would she need compounded weekly if she were to have exactly $1,500 in 10 years? Again, I hear that word compounded. So I know we need to use the compound interest model. But what parameter am I solving for in the compound interest model? PV, FV, R, K, N. Solving for R this time because it's asking for the interest rate that I need. Okay, so let's start filling everything else in. Future value should be 1,500. Present value is 600. K is, what is the K here? 52, great. What word told you 52? Compounded weekly, good. And then the N is 10. All right, so to solve for R, what's the first thing I should do? Divide by 600. If I reduce that, that turns into 5 over 2. You could call that a decimal also if you wanted to. And then I'm going to multiply some of this other stuff out that I can. Okay. To get the R by itself, then, I need to cancel out that exponent of 520. What can I do to both sides to cancel out that exponent of 520? Not a logarithm. A logarithm is going to cancel the exponent base. What's going to get rid of the exponent self? Not a natural log. What if that was just an exponent of 2 up there? How would you get rid of that exponent of 2? Square root, right? So what am I going to use here? Just the 520th root. So then to get the R by itself, I just need to subtract 1 and multiply by 5,200. And that should be my value for R. Reminder to type in a root of your choice index, like the 520th root. I'm going to type in the number 520. Then I'm going to press math and choose option 5. And just do that. So I get about 9.17.
I know. Were there any? Oh, I can't wait for that to no, I knew I would have it.
Okay. One more model to talk about. This is the continuously compounded interest model. Here we have that FV is equal to PV times E to the Rn over 1,000. I'm sorry, over 100. So again, FV still future value, PV still present value, R still interest rate, N still time. What is E? That's a constant, right? That was a number that's at like 2.78, yada, yada, yada number we talked about earlier. So that's just a constant. It's built into our calculator, so we don't have to worry about it. But that's a funny formula. Like, why is the E coming in here? Right? This is still says it's a compound interest formula. So if we're compounding continuously, what should the K have been? Let's see how we go from the compound interest formula to this formula. What does compounding continuously mean? Stop talking, please. How many times per year is interest compounding if it's compounding continuously? Pick a number, take a guess. I'll play over or under for you. More. More. More.
Million.
More. Ah, there you go. Infinite. Yes. Okay. So that's what we're talking about, where K is, we're having an infinite number of compounds per year. And now recall, when we defined E earlier, we said E was the limit as x goes to infinity of 1 plus 1 over x to the x, right? That was part of our definition for E. So what I'm going to do now is I'm going to take our compound interest formula and turn it into our continuously compounding interest formula, assuming that K goes to infinity. So I'm going to start by making a substitution. I'm going to say X is going to equal 100K over R. So I have R over 100K. So if that's the case, then that I can rewrite R over 100K as 1 over X. Everybody's good with that? because they're just reciprocals of each other. Next, what I'm going to do is I'm going to multiply this numerator by 100r over 100r. Is it okay for me to do that? Yeah, why is it okay for me to multiply the exponent by 100r over 100r? Because I'm just multiplying by 1, dude. Like, that doesn't do anything, right? No big deal. And you're asking, looking at me like, why in the heck are you worrying about multiplying by 1 here? Well, what I'm going to do is I'm going to take this part and group it together. And then I'm going to take this part. Oops, that's not right. Hold on. Is I'm going to take this part and group it together. And I'm going to take this part and group it together. And you might be looking at me like, okay, but like, why group that parts together? Well, that stuff in the, like the periwinkle blue, notice that's just X again, right? And as X goes to infinity, then that piece just turns into E. Hi, Mr. Whalen, what's up?
Just
Delivering notices?
like at 2:30.
Sure.
Thank you very much.
Yeah. Zach, you got a visit to make. For counseling? It gets an ooh? Oh, that's a woo. Yeah, probably. Well, if you run under 100, under 11 seconds in the 100 as a high schooler, that's legit fast. That's legit fast. Like, nobody's going to argue with that. It's like,
Well, I mean, if you go down to Texas, they got like 10 ones.
I understand,
Take that.
but like, everybody understands that Michigan isn't Texas because you have winter, and that's a problem.
Exactly.
All right. Last example, and we're going to be outie. Sound good? All right. Jack invests $800 into a savings account with a 5% annual interest, compounded continuously. That's the key phrase for me. How long will it take Jack to have $500 in interest? All right, which parameter am I solving for? FV, PV, N, or R? It's asking how long, so that's time. Remember before, when we're solving compound interest formula for time, what are we going to end up having to use? A log. So I know that's going to be coming somewhere. What's my present value going to be? 800. What's my future value going to be? Not 500, because notice it says 500 in interest. Yeah, so that should be the present value plus the interest. So that's going to be 1,300. And what's the R going to be then? That's just our interest rate. So let's fill it in. 1,300 equals 800 E to the 5n over 100. First step should be to you divide by 800. When I reduce that fraction, I just get 13 over 8. And at the same time, I'm going to reduce the fraction 5 over 100 in the exponent there, just to make that n over 20. All right, what do I need to do next? No multiplication. How do I cancel out that exponent base of e? I need to use a log. Great, which log? Log base e, which is the natural log. Yep, that's correct. Very good. And then we just need to multiply both sides by 20. And we're good. In a scant 9.71 years, we'll be at our goal of $1,300. Okay. That wraps up everything I needed to do with you guys today. So I think we left off at 138 was the last homework problem that I had assigned. I'm going to add on today 139 to 150. And that'll close us out for today. Sound good, my dudes?